This tutorial will show you how to create a physics-based character controller with a grappling hook in Godot 4 using C#. The video is split into two chapters, one for the physics-based character controller and one for the actual grappling hook. If you already have a rigid body character controller like the one from my mini planet tutorial, you can skip straight to the grappling hook chapter. If you are feeling impatient, the source code is available on my Patreon. Link in the description. Okay, so I've started with a fresh Godot project. First thing I'm going to do is project settings. I'm going to get scene name casing, and I'm just going to change it to Pascal case. I like to always do that since I'm using C#. Class names are in Pascal case, and I want my scene names to match the classes that get attached to them. First thing we're going to do is just make the world environment. So if you already have a level set up, you can skip to the next chapter. So we start with our world as a node 3D. We're going to add a static body 3D. This will be our ground. We'll add a collision shape 3D with the world boundary shape. Let's just make sure that we can't fall out of bounds. And we're going to add a mesh instance 3D. Going to be a plane mesh. Let's make that 100 by 100. Give ourselves plenty of room to work with. I'm going to import some assets that I have. I got this from a free texture website that I forget the name of. I will put it in the description. I have a grass texture and a rock texture. I'm just going to use this so that our scene isn't too bland. So just dragging that in onto my ground mesh instance. And I'm going to go into it under geometry. There's the material. Scroll down to the UVs. And I'm going to just bump the scale way up on that so that the ground looks a bit better. Next, I'm going to add another static body 3D, mesh instance 3D under that. I'm going to put a box mesh, bump this up to a 4x4x4 cube, and if you click on mesh up top, create collision shape, placement sibling, type trimesh. I'll just immediately make a collision shape for us. I'm going to give this my rock texture, and I'm going to click Control D to duplicate this a few times. Just put some obstacles around our environment that we will be able to use our grappling hook on once we've implemented it. So that's the geometry of the world done. Next, we just need a quick world environment node. We click New Environment, click on the environment. For the background, instead of clear color, we're going to do sky. This gives us the sky dropdown, where we will do new sky. And for the sky material, we do new procedural sky. In our world environment, if we scroll down to ambient light, currently since the sky is bluish, we get a bit of a bluish ambient light in our scene, which we don't necessarily want. So we're going to change the ambient light source to color, and we will make that color white. Lastly, for our world, we will add a directional light 3D, tilt it at an angle, and let's turn on shadows. That is our world done, so we can save our scene. Now we move on to the player. So we're going to do new scene, 3D scene. We will change its type to a, my caps lock was on, to a rigid body 3D. And we will rename it to player. We'll save our new scene. On our player, we're going to want a mesh instance 3D. I suppose we don't need this because the game's going to be in first person, but force of habit, I have to do it. We will use the capsule mesh, and we add a collision shape 3D, set the shape again, capsule shape 3D. Now to check if our physics character is standing on the ground, since we're using a rigid body instead of a character body 3D, we have to check our grounded state manually. For that, I'm going to use a shapecast 3D. Set the shape to a cylinder. Here's our cylinder. We're going to decrease target position, say down to negative 0.2. And if we click on our cylinder shape, we can decrease the radius just a bit to 0.45. This way, if we're pressing up against a wall, it doesn't count that as us standing on the ground. We will rename this to Groundcast. Next up, we need a camera. We will move this up a bit so that it's positioned where our head would be. And on our camera, we're going to put a color rect. This, of course, doesn't have to be on the camera because this is just going to be a 2D object, but since it's being rendered on our camera, I'm going to put it on the camera. So if we click Layout, Transform, we can set the size. We'll set this to 4x4 pixels. Up here for the anchor preset, we'll put it in the center of the screen, and this will be our reticle so that we can see what we're pointing at when we use our grappling hook. Now we need to add our controls. So we're going to go to Project Settings, Input Map, Add New Action. We are going to need forward, bound to W, backward, bound to S, left, bound to A, and right, bound to D. Jump, bound to spacebar. We will do grapple, which will be bound to our left mouse button. And finally, we will do pause, which is bound to escape. You don't really need to set up pausing, but it's a nice quality of life thing. Now we add a script to our player. Of course, this is a C# tutorial, so we're going to do it in C#. We can get rid of the boilerplate code for now, and let's start defining some variables. So first, we want to be able to set our acceleration. I'm going to set this to 100. I want to set our max speed. So this will be our maximum velocity as we go across the ground. I'll set that to 5. We are going to want access to our shapecast that we made, that we called Groundcast, and we're going to use that to check if we are grounded. And for that, I'm just going to write a property that just checks groundcast.isColliding. Just makes it a bit simpler to later on call isGrounded instead of always having to call this, and then maybe you want to implement something like coyote time or otherwise change how your grounding works, and then you just have to change this property instead of replacing every instance of where you checked it. Next, we want some movement control when we're in the air. So I'll call that air movement modifier, and I'm going to set that to 0.2. I'm going to add our jump impulse. I'm going to set that to, let's say, 12. And we're going to come back to declaring variables in a bit, but this is enough for us to get started with allowing the player to actually move around. So now we write our physics process method, and we want to be doing this in physics process, not process, because this is a rigid body and we're going to be moving our player using physics. I'm going to declare a variable called direction. This is the direction that the player is trying to move in. We need to define which direction is forward. Now this is going to depend on the rotation of our player character. So for that, we check the global basis of the character, and we get the Z component. And it is negative because in Godot, negative Z is the forward direction by convention. And then similarly for left, we're going to do the negative X direction. Now we start applying our inputs to our direction. So I'll write it like this instead. If input.isAction pressed forward, direction plus equals forward. If backward is pressed, then we do minus equals the forward direction. And I'm just going to copy paste those again, except with left and right. And for those, we instead add or subtract the left direction. Now lastly, we want to make sure that direction is normalized. This way, if you're moving both forward and to the right, say, if you don't normalize it, you would actually go faster when moving diagonally than when moving in a straight line. We don't want that. We're going to check, are we grounded? If we are grounded, we want to ensure that the player doesn't run faster than the max speed that we set. So to do that, first we project our velocity onto the direction that the player is trying to move in. So if we are not moving, then that's quite simple. It's just equal to our velocity. However, if we are moving, then we do linear velocity dot project onto direction. Next, we want to check what is our player's current speed, and that is just the length of the velocity vector. And then we're going to say, okay, if our direction is not 0, that is, we're trying to move, and our current speed is greater than our maximum speed, and the angle between our current velocity and the direction that we're trying to move in is less than pi divided by 2. So that is to say, we're trying to move relatively in the direction that we're already moving, meaning our speed would further increase, then we want to decrease our input in that direction. So for that, first we do our current speed divided by our maximum speed. So this is sort of, the percentage of how much we're trying to go in that direction. And then of course we take the direction we're trying to move in, we project it onto the direction that we're already going in, and we make sure to normalize that. And so this ensures that our input is not adding any more acceleration in the direction that we're already moving in. That's if we're standing on the ground. If we are in the air, we're not going to do any of this sort of velocity limiting type stuff, but we are going to apply our air movement modifier. So we have less control over the direction that we're going in when we're in the air. And you can, of course, adjust those parameters to your liking. Now we apply a force in the direction that we're going in, multiplied by the acceleration. That's one of our exported parameters. And we multiply it by the mass, because force is mass times acceleration. Of course, our mass is only 1 kilogram. You probably aren't going to change the mass much, but if you do, there you go. It's accounted for. Now let's check if we're jumping. So action just pressed jump. And we are on the ground. Then we apply central impulse in the up direction times our jump impulse. And now lastly, we're going to look at our physics material override, where we can change the friction that our character experiences. And if we are on the ground, I'm going to set this to 2. I think the description says that the value goes from 0 to 1. That's not true. It can go greater than 1. And I find that the friction when it's equal to 1 isn't that good. You still tend to slide around a lot. So we're going to bump that up to 2 when we're on the ground. And when we're in the air, we're going to make it 0. Because if it's not 0, you can sort of stick to walls as you're falling. And we don't want that. Okay, so that's good for now. We're going to build our scene. Make sure that we set our ground cast. Make sure that we make a physics material override for our player, since then in the script it'll either set this friction to 2 or 0. I'm going to set it to rough. We're going to add a bit of bounce so that we don't just slam into walls as we're grappling around and then instantly stop. That feels a bit weird. Then we're going to scroll down to physics body 3D axis lock, and we are going to lock our rotation on X, Y, and Z. We don't want the player character to be falling over or anything like that. We don't want to do physics for our rotation. If we go back to our world, we can now add our player to the scene, lift them up off the ground a bit, and if we hit play, no main scene has been selected. We're going to select current, and there you go. We can now walk around in our scene. Jump impulse might be a bit too high, but that's fine. When we're in the scene, our mouse cursor is free to move around, which is a bit annoying. So let's go back to our world scene, and I'm going to add a child node, literally just a node, and I'm going to call this pause manager. And under process mode, we're going to set that to always. So this node runs even when the game is paused. Attach a script to that. We are going to make a method called public void set paused. which takes in a boolean whether or not it is paused. We do getTree.paused equals paused. This allows us to pause or unpause the game. And now if the game is paused, we do input.mouseMode equals input.mouseMode enum visible. So when the game is paused, we can see our mouse and move it around. If the game is not paused, we will capture the mouse so that it follows our cursor, or so that it's stuck in the middle of the screen and is not visible. In process, we will check, is action just pressed pause? And if so, we will set pause to basically the opposite of whatever it currently is. So if the game is paused, then we set unpaused. If the game is unpaused, we set paused. And then in ready, we will just ensure that the game is immediately unpaused. So now if we load back into the game, you see you can't see my mouse anymore. I jump up in the air, I press escape, the game is paused, my mouse is free, I can exit. Now we can go back to our player script, and let's set up the mouse controls. First, I'm going to track a vector2 that I'm calling mouse delta, and this is going to track how far your mouse cursor has moved on the screen since the last update. I'm going to add a public float mouse sensitivity that we can change in the editor. I'm going to set that to 0.5. I'm also going to check the X rotation of the camera. So this is the rotation around the X axis, so basically looking up and down. And that's because we don't want to allow the player to look up more than 90 degrees or look down more than negative 90 degrees, because then you could look behind yourself, and that's just no good. And lastly, we get a reference to our camera. And scroll down to the bottom of our script, and I'm going to make a private method that we're going to call process look. It's just so we can divide up our file, make it a bit more readable. Now we are going to check this delta x. Now this is a bit confusing. So this is delta x because it's the rotation around the x-axis, but that is due to the y movement of your mouse. So a bit confusing there, but we'll go with it. And this is just that value multiplied by our mouse sensitivity. And now delta y is for the y rotation, which is looking left and right. We're using the x position of the mouse. We're making this negative just because otherwise it's inverted. Now, okay, so rotate y, we're doing rotate object local around the up axis, and we are doing degrees to radians delta y. So our mouse sensitivity is in radians, or in degrees, and this is just going to rotate our player around the up axis so they're facing the right way. Next, we're going to look at our camera X rotation, and we're going to add our change in X angle to it. And like I said before, we're going to make sure that this is within the boundaries that we've set. So it's either greater than negative 90 or it is less than positive 90. And if that is the case, then we rotate our camera around the x-axis by delta x. Again, the sign is just so it's not inverted. I don't actually, off the top of my head, I can't tell you why we have the negative signs where we do. It's just you put the values, you see it's inverted, you put a negative sign, you move on with your life. And now after we've finished processing this, we're going to reset our tracked mouse movement, our 2D mouse movement. Whoops, not X. And now, of course, we need to actually set this. And the way we're going to set this is in the input method. We can check if the input event is a input event mouse motion. So if the game just saw that the mouse moved, actually we can do that in line here. So if the event is this input event mouse motion that we're calling mouse motion, then we do mouse delta plus equals mouse motion dot relative. And lastly, we have to make sure that we actually call process look at the end of our physics process method. And we go back in here, we rebuild. Want to make sure that we assign our camera. Now we go back into the game, and now I can actually look around. So that's our basic setup done. Now we're able to actually do the point of the tutorial, which is to make the grappling hook. So let's make a new scene, 3D scene. We're going to call this grappling hook. I'm going to add a node 3D to this. Then we're going to call rope root. We're going to see why I'm doing that in a second. We add a mesh instance underneath that we will call rope. We will give this a cylinder mesh. Shrink the top and bottom radius down. For the radial segments, since it's so small, we don't need such a high resolution, so I'm going to drop that down to 6. You can hardly tell. And the number of rings, so this is the number of mesh segments moving up in the Y direction. I'm going to set that to 60, and that's because we're going to animate our rope later, so we're going to want to actually have some vertices in there that we can change. I'm going to rotate it down. Actually, no, I should have rotated it this way, because the negative Z direction is what we've defined as forward. I'm going to shrink its height to 1, and I'm going to move it forward. We're going to make sure that that's a bit more precise, so exactly half in the Z direction. So now the reason we have it set up like this is now if we click on rope root, transform, unlock the component ratio, and now if we scale it in the Z direction, we can see that basically whatever number we put in here is going to exactly correspond to the length of our rope. So with that done, we can make our grappling hook script. So firstly, we can do the visuals for our grappling hook. So we want the node 3D that was the rope root, and we want the mesh instance that was the rope mesh. We are going to check, are we currently grappled to something? We are going to record the physics body that we have grappled to, and we are going to record the grapple point local position. So this is the position relative to the target that we've grappled to, that our grapple is attached to. If you're only ever going to grapple to static bodies that aren't moving, then you can just record the global position and not bother with this, but this will allow you to say you want to grapple onto a moving rigid body and follow along with it. Then you have to track where that body's moving and then track where you grappled to relative to that body. And now let's make this an export. We want the rigid body 3D that is our player, and we want the acceleration imparted by our grappling hook. So when you grapple to something, you will accelerate towards it at 5 meters per second squared, I guess. I'm not I'm not sure what the units actually are. Next, we can write our ready method. All we're going to do here is make our rope invisible, and we will then set it visible when we actually do the grappling. Now we write our physics process method. Again, it's physics process because we're applying forces. And here I'm going to write 2 methods. We're going to have process input and process grapple. And I will call both of these from here just to split up our script a bit, make it a bit more readable. So in the input, this is just where we're going to check what we do when the player just pressed the grapple button. So firstly, if they're already grappled, then we want to turn the grappling hook off. Now when the grappling hook is off, we don't want to see the rope anymore. We want to reset our tracked position to 0. We want to set our target to null, and that's it for now. The other option is we've just tried to grapple and we are not yet grappled to something. So in this case, we basically want to raycast from our grappling hook to whatever our target is and see if we hit something. So for that, we do from our positions. This is the position of our grappling hook. Now you could probably change this to instead be the camera position from the player, but I'll just keep this simple for now. The forward direction is going to be this.globalbasis.z. And again, it's the negative Z direction because that's forward by convention. So we have basically, this is from is where our raycast is going to start, and then 2 is where our raycast is going to end up, and that's going to be the position of the grappling hook plus the forward direction times 500. So this is sort of the range of how far away you can grapple to something. You can change that to whatever you want. And now we actually do our raycasting. So to raycasting code, first you need to get the world 3D, get direct space state, and then you can call intersect ray. This takes in a physics ray query parameters 3D object, which you can create by calling create, and you pass in from and to. Now the way this works is a bit weird. What it gives you is a Godot dictionary and not some sort of raycast result object. So what we have to do is we check, does this dictionary have any keys? And when I just put any right now, that added this import. So make sure that using system.link is there, else this code will not work. Because basically what they do is if you didn't hit anything, it returns an empty dictionary with no keys. And if you did hit something, then you get a dictionary with keys. Now what we want to do is first we want to see what did we hit. So we do node 3D raycast result collider. So this gives the collider that you hit. I think instead of giving like the collision shape 3D object, it gives a physics body 3D. I think it could also hit an area 3D, depending on how you have it set up. So I just ensure with an if statement that we've actually hit a physics body 3D. So here we say if the node that we hit is a physics body 3D that we're calling hit physics body, then we say that our grapple target is going to be that physics body. Our grapple point local position is going to be hit physics body dot to local. So this converts a global vector into a local vector. And the vector that we're going to pass in is raycast result position. And you see that we have to explicitly cast this to a vector 3 because it returns a variant parameter. Now we say is grappled equals true, and we set our rope to be visible. So now with that set up, we can save our grappling hook scene because I forgot to do that earlier. We can rebuild. Now we can assign our rope root, our rope mesh. We can't assign our player here, but if we go back to our player scene under our camera 3D, we can add our grappling hook scene, and let's move it a bit to the side, move it a bit forward so it's not blocking our view. We can save that. And now from here, we can assign our player. So let's go back into our script and set up process grapple. So do if is grappled. We first want to convert our local position into a global position. So to do that, we do grapple target dot to global of our local position. We want our grappling hook to look at that position. We can do that very easily with the look at method. Now we want to see how far away is that point. For that we do global position minus grapple point global position. And this is the displacement vector from our grappling hook to our target. Now we can scale our rope to be vector 3 with the displacement length as the Z component. So as we showed before, that's just going to scale up our rope so that it reaches the whole way to our target. Now let's make our grapple actually do something. For that, it's quite simple. We do player.apply central force displacement.normalize. So this is basically the direction. Multiply that by negative acceleration times our mass. So multiplying by the mass turns an acceleration into a force. And this is negative. Because of how this is set up, I guess I gotta flip these, made this not negative, but that's fine. There's one last thing that I forgot. So in here, since we're pointing our grappling hook towards the position, we need to reset that when we stop grappling, else when we do our raycast, we're using that old direction. So in here, we just do this dot rotation degrees equals vector 3.0. Okay, and now we can grapple onto whatever we want. Now our grappling hook, frankly, looks kind of bad. So let's go about making it look at least slightly better. First, I'm going to add some mesh instances. Now, ideally, you would instead have a nice grappling gun model. But since I don't have one of those, I'm just going to make one out of cubes. So let's say this is the barrel of our grappling gun. We add another mesh instance 3D. Another box. There we go. There's our beautiful grappling gun. Now for our rope, we're going to make the rope look a lot better. First, actually, I'm going to decrease the radius just a bit more so it looks more in line with the gun. And we are going to create a new shader material for our rope. We'll use the default name. Open this up. We don't need to do manual lighting on it. So in our fragment, this is for the appearance of it, or the texture of it. We're going to set our albedo texture to black, which is just all zeros. Now, I'm going to make, this is just a temporary variable. I'm going to call it progress. It'll be time modulo 1. So this will basically be, as we shoot the gun, we'll have a value going from 0 to 1 that'll sort of play out an animation. And for now, I'm going to have it just loop so I can actually see what I'm doing. First, we're going to have the gun, or the rope, extend. So for that, I'm going to set the Y component to be Y times this progress value. So you can sort of see there that it's extending. However, it's doing so from the middle, which we don't want. So to fix that, all we have to do is subtract the progress. Now it's going too far. Progress divided by 2. That's going the wrong way. So we will do 1 minus the progress divided by 2. Sort of flip it around. Now it's extending out in the right direction. Now we don't want our rope to just move so statically. So we're going to add a bit of a sine wave to it. So in the X direction, we're going to add bit of a curve to it. So what this basically does is the X direction, at least in its local space, seems to be up and down because remember we've rotated this cylinder around to face the negative Z direction. So this gives it a bit of a sine curve to it. You can adjust, how many bumps there are by changing this value. And then this is the amplitude. And now to make it actually look a bit better, we're going to change the amplitude over time. So we will now set that to a separate variable, and we're going to multiply that by the sine of our progress, say times 3 times pi. So has it looking a bit better. If we adjust this, we basically change the speed that it wobbles at. I think 3 is pretty good. And then lastly, we're going to sort of fade out the amplitude by multiplying it by 1 minus the progress. So now this is going to be a value going from 1 to 0, 1 when it just started, and 0 when it's done. So there we go. Now we have a bit of an animation. Now instead of just using the time value, looping forever, I'm going to define a uniform called progress, and this just means we can assign this value in code. Now if we go back to our grappling hook, all we need now is a reference to our shader material we just made called rope shader. We are also going to want a variable called grapple extend time. So this is going to be how long, will be the duration of that animation. So we'll say half a second. And we're going to want to track how much time has passed. So this is how far along we are in that animation. To get our rope shader, we do rope shader equals rope mesh dot surface get material 0 as shader material. So I'll just grab our material for us. Now in here, basically when we are resetting our grapple, we just want to make sure we reset our animation. So this is the time that the animation is playing at, so we just reset that. And now down here, where we're processing our grappling hook, we will do grapple time equals the minimum value. Before we get to that, we need to pass in the delta time value from physics process. So we pass that into process grapple. So now we add that value to our grappling time up until we reach the maximum value, which is the time it takes to fully extend. And then in our rope shader, we set shader parameter progress to the grapple time divided by the grapple extend time. That's just sort of normalizes it between 0 and 1. And now with that, if we go back into our game, we now see a nice animation when we grapple onto something.